Hello, Kai. How are you?
That's T. Pretty good, even though I still can't open my window.
Oh yeah. So is it super smoky or just like is there burn stuff nearby or tell me about what's going on?
The air quality is still bad in
Yeah.
my area. It's like moderate from what it
Hmm.
is, or like it's around 97, I think, which they say don't go outside if you could help it.
Yeah. Yeah. Yowie.
Yeah.
Yikes. My goodness. Oh, and let's see. Screen here. Ooh. Um, that's my wife. She's gonna run away. You guys got to see her. So, yeah, I mean, I don't know because the air's been, I'm in like, I'm sort of like Campbell, San Jose. Like I'm where, I'm about half a mile from where 17 and Camden intersect. There's Camden turns into Santa Moss. There's
Uh,
Highway 17.
yeah.
Yeah, that's where, when you like, if you go into Santa Cruz, you'll pass that exit before Los Gatos and then you hit the hills.
Huh.
And the air's been terrible out here, but I don't. But we're not really. I think if you go east, if you're on the east side, then you're closer to the fire, right?
Yeah, I'm by like Southside San Jose, Morgan Hill area.
Okay. Yeah. Well, the fires are southeast, right? And there's there's Henry Coe State Park, right?
Oh yeah, that's like right by where I live.
Right, right, right,
I live by at the bottom of Mount Hamilton, like on
right,
by
right,
on Evergreen.
right.
Is that still on fire?
No, it's not. It's just really smoky now. They pushed it more to the other side of the mountain, I think.
Okay, because I go fishing and hiking in Henrico all the time, and backpacking.
Oh, that's so cool.
Yeah,
That
but
is so cool. Yeah, I don't know. You see, I'm actually afraid to ask because I have a friend who has a cabin out in Henrico State Park. It's like there's certain parts of it that you can purchase, right? And he purchased this one hill and he built a cabin on top. And then about 12 years ago, it completely burned down. There was this horrific fire. And it was started by a guy burning trash. He has a neighbor, like 5 miles away or something. And it completely burned down this huge cabin that he'd been working on for a long time. And and then, oh my gosh, somehow he got up the gumption and he rebuilt the whole thing. And I'm afraid to ask him if it burned down again, because it would just be so terrible.
Yeah. I would go hiking like almost every weekend at what is it called? Portola area. And now it's all burned, like Portola redwoods and
Oh wow.
yeah,
That
and
is that
like
on the
San
other side of
Mateo.
the Oh,
It,
sorry.
it it's like San Mateo, Pescadero Park or something
Oh,
like that.
right, 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 right.
And
Oh. Oh,
yeah,
right, 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 right.
all of that
Portola
burned.
Creek. Oh
Yeah,
my
so like
God.
from Portola to like Big Basin and stuff, and
Oh,
or like
geez.
Castle Rock, it's all like it like burned down, I guess, all that area.
Oh my God, that is crazy. That is so crazy.
Yeah, but they opened it.
Uh,
They just opened it again.
really? Oh
Yeah,
my gosh.
I know. I want to go back. I left my stick there. You know, the one that you
Oh,
use to hike to walk.
Your hiking stick?
My hiking stick, yeah. I left it there and I was just like, I wonder if it burned down.
All right. I wouldn't get my hopes up.
I even took a picture of where I left it. I was like, I'm gonna come back for this hiking stick. It was really good.
All right. Well, I hope it's okay. I hope it's okay.
Same.
Oh God. So now it's so cool that I'm seeing faces now. And you know why I can say I see Dan, I see my own face, I see Ivy, Adam, Kenya, Calvin, Ikun, Carla, Kai, Richard, I don't see, Leslie, I don't see, Pauline, I don't see, and Lily, I don't see. But
My internet's really unstable, so I probably shouldn't turn mine on.
oh, okay, that's cool. That I completely there's Richard. Richard is in the tropics. Oh, that reminds me, I spent some time in Cancun and Cozumel and Tulum, these three cities on the Yucatan. And they literally, it was just like that. It was just like white sand going into aqua water and like palm trees and coconut palms and it was just so amazing. This was in the 1980s. We just drove down there in a van, in this camper van, and we just camped on the beach.
That sounds awesome.
It was totally awesome. I mean, when it wasn't completely miserable, it was totally awesome. But it was, I kind of wish I could do it again, but I don't think it's really the time anymore. But so the reason I was saying that it's cool that I'm seeing a lot of faces, and Calvin's back, is that I feel more compassion, so I feel embarrassed for the trap I was going to spring on you guys. So maybe I'm not going to spring it. We're just going to have to wait and see. If I see plenty of faces, maybe I won't spring it. Yeah, so we'll just have to wait and see. But so you guys see the single molecule fluorescence thing up now? That's what you see on Zoom?
Yes.
Okay, cool. So now somebody bring me back up to speed in what we're seeing there. In terms of this, seems like a lot of you knew what the F1 ATPase was. And it actually spins around, I guess, in the presence of ATP. Is that correct? Who said they knew?
It like puts it together. It puts ATP together, I think.
It creates
okay.
ATP.
I wonder what makes it spin around then. Interesting. But in any case, this spinning motion, right, is captured by this fluorescence anisotropy. And silly wife is blabbering away there. So how is the fluorescence, or how is the rotation captured using the fluorescence of this molecule? Who can answer that question for me?
Wait, can you repeat it again one more time, please?
Sure. How is the rotation? I keep giving away this stupid answer. How is the rotation measured or captured or detected using the fluorescence of the single molecule?
Is it the magnetic field?
Oh, this is good. This is good. Using your intuition. Yes. But not true. Not true. There may be a magnetic field on the molecule, but it's nothing. I don't know why they have these stupid magnetic field lines there. That's just ridiculous. Because there's no the Psi3 molecule is not a magnet. There are no magnetic field lines like that. I don't know, somebody who didn't probably know a whole lot about the physics of this thing, or they found this cool like clip art or something of a light bulb with those lines, but it's not, has nothing to do with magnetism. Now, it is spinning around this axis, right? The axis of the, let me see. I can't redo that thing, but it is spinning around an axis here.
Oh, so then is it the rotation?
Yeah. So what does the rotation do? You know, how is the rotation detected, basically? That's the question.
Didn't they attach a probe to the rotor in the middle, and then every time or at different iterations of the rotation, it hides the rotor in the middle, so then they would see it fluoresce and then disappear, and then so on. Maybe.
Oh, I like it. I like it. I like it. It's so close. It's so close.
Is it due to like when it rotates, the light's polarized in a different way, and it only reads it at a specific like polarization?
Yes. That was you, Ken. You're right.
It was Carla.
Oh, hey, Carla. There you are. Sorry. Yes. You guys are just like, you guys are like fighting an invisible dragon, and you're taking these swings, you know? And they
type on the chat.
Yeah, you
Alvin said polarization a while.
Calvin said polarization. It's all close. It's all close, you know? But it's not quite there. So Aditya said that the fluorophore, when it rotates, it hides, right? And that's close. And then Carla said the polarization rotates, right? Carla?
Yeah, essentially.
Okay. And that's true in a sort of a reverse sense.
Is it the electric field rotating relative to the incident light?
Electric field rotating relative to the incident light. Very, very close, yes. So the molecule has, so the molecule is tied on to the protein in such a way that its transition dipole rotates along with the molecule, right? So there's one sense in which this makes sense, one sense in which this works, right? That it rotates like this, right? It rotates around its long axis, you know? If it's just spinning, it doesn't make sense, you know? That doesn't, can you guys see my tiny little picture playing with my pen?
Yes.
So that doesn't make sense. But if it rotates around like this, then that's the molecule and its transition dipole moment. They're just kind of like the same thing, right? They rotate around like this, right? Now, the light polarization is fixed. The light polarization, let's say the light is polarized along this axis. Say the light is polarized right vertical, right? Then as this molecule transition dipole becomes orthogonal, it goes dark. When it's in plane, it's bright. It's dark and it's bright. It's dark and it's bright. Does that make sense? When the transition dipole and the electric field vector of the light are coincident, then the fluorescence is high. Does that make sense? Ikun, does that make sense?
Yep.
Okay, cool, good. So that is what you see in this half-second set of frames here. You see dark, light, dark, light, dark, light, dark, light, dark, right? And what you can do with this is you can make a sort of a frequency plot of the polarization anisotropy And then you can use that to calculate the frequency of the rotation, right? So, let's see here. So this is an example of single molecule dynamics using using fluorescence. So let's take a little bit different cut on this. How long is this time? This total time duration, let's say this is 2 seconds. Does that make sense to everybody? From the start here, I don't know, maybe it's 6 seconds. I can't tell if there's like 1 or 3 or however many. It probably goes left, right, left, right, left, right, left, right, left, right, right. And then there's this arrow, right? That's seen rotating here, right? And that's the polarization vector of the light, or of the transition dipole moment, right? So this is the polarization of the transition of the molecule as the molecule rotates. So if it takes a half second, if like from this point to this point is a half second, let's say, then answer me this. How many fluorescent photons could we collect in 1 second from this molecule approximately?
Wait, can I ask a question?
Yeah.
So when the polarization is correctly aligned, is it only a single photon that goes through, or is it multiple?
Excellent question. Excellent question. I love it. Who can answer it? Is it a single photon? Can we detect a single photon? Yeah, but statistically, it doesn't mean shit if we detect one photon, right? To get A, above noise, above the noise background, and B, get a clear distinction between the two polarizations, we need 1.3 metric buttloads of photons, right? So we need at least 10,000 photons at every point, right? Every frame has to be at least 10,000 photons. Why do I say that? Because the square root of 10,000 is 100, and the signal to noise ratio, best case scenario, will be 100 under those conditions if you collect 10,000 photons. Best case scenario, your signal to noise ratio will be 100. This is probably more like a signal noise ratio of 10, but still it's probably around 10,000 photons. Because in this case, there's a lot going on, right? First of all, the little spot that you see in this tiny little diagram, the tiny little spot is probably a micron on a side. And how large is a molecule? Is a molecule 1 micron on a side? Aditya, how large is a molecule?
Like in the angstroms?
Yes. Isn't it? How many angstroms in a micron? So how many nanometers in a micron? Important to know. There's 1,000 nanometers per micron, and there's 10 angstroms per nanometer. Where did this stupid ass angstrom unit come from? It came from the size of the helium atom. The helium atom is about 1 angstrom in diameter. and it's like crystallography thing. So these boxes, even though they fill with the light from that single fluorophore, are approximately 1 micron in diameter. Because when you do microscopy or when you do microscopy and telescopy, whoa. When you do those two things, you always see blobs of light that are way, 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 way bigger than the thing that emits the light. Right? So why do all the stars and galaxies look the same size to our eyes at night, even though they're gigantically different in actual size? Because when light is distant, we can only resolve a certain size, right? The same is true under a microscope. Under a microscope, even like the things that the source of the emission in this is literally a one nanometer piece of real estate that's rotating, right? But when it comes out through these lenses, the best you can do is image it to about a micron, maybe a half a micron. And that's called the diffraction limit. Right? That's the diffraction limit of light. So this box contains enough space for, let's say, 1,000 by 1,000 is 1,000,000 of these stupid molecules. But how many of these molecules are in this box? How many? Pauline, Leslie, Lily. Contributions. Ivy.
Which box?
Okay. In these little
Oh,
picture boxes that are about 1
any
micron on the side, how many
Oh,
molecules?
just any box.
Well, no, specifically these boxes here, where they've taken a photograph of the brightness of the image of this molecule. How many molecules are in that box?
1.
1, exactly. Exactly 1, right? And it looks larger than it is because it looks the far field limit of the far field diffraction limit there is about half a micron. Does that make sense, Calvin? I'm sorry if I'm like beating a horse. I'm trying to engage y'all in the conversation a little bit because it's more fun for me. Kai, how are you doing? Kai. Yes, I'm talking to you, Kai. Check
Yes.
out Kai. How are you doing, buddy?
Good.
Yeah?
Yeah.
Are you listening or did you mute me?
No, I'm listening.
Okay. All righty. So, how many photons are collected in any given frame here from, how many fluorescent photons from this little twirly bird here? A minimum of, how many photons, anybody?
10,000.
10,000, right. Because you need to get at least 10,000 photons to be above the noise floor and to get adequate signal to noise ratio. Okay. So how long are these? They're probably 10 milliseconds per exposure. Right? 10 times 10 to the minus 3. That's 10 to the minus 2 seconds. So what if I were to tell you that the fluorophore lifetime here was 10 to the minus 2 seconds? What would you tell me? if you were feeling rambunctious, like Carla.
Can you repeat the question again?
Yes. What if I were to tell you that the fluorophore here, the Psi3 that is tethered to the ATPase, has a lifetime, a fluorescence lifetime of 10 milliseconds?
Does that mean every 10 milliseconds the fluorescence like turns off essentially?
Oh, no,
Is that
that
what I'm
means that
understanding?
so in order to fluoresce, the molecule absorbs a photon, enters an excited state, and hangs out there before it emits a photon. And I'm saying in this case that it hangs out there for 10 milliseconds before it emits a photon. Calvin, what do you tell me? Oh, Ivy, I'm sorry. Yes. Richard Pearson says, is that too long though? I thought it was 10 to the minus 4-ish. Well, 10 to the minus 4 is closer, right? That would give you, in every 10 milliseconds, then you'd have time to collect 100 photons if you could collect every single photon. But the lifetime of this fluorophore is more typical of fluorescent molecules. And this is, lifetime is about 10 to the minus, how many milliseconds? Or seconds, how many? 10 to the minus how many seconds? Dan. What's the exponent? 10 to the minus blank seconds.
Sorry, you lost me with all the exponents. Well, if there's in a second time, that's 1,000 milliseconds, right? So then that would be 100 in a second.
Okay, 100 in a second would be 10 milliseconds.
Yeah, sorry.
Okay, so the answer for any fluorophore is 10 to the minus 9 or less or shorter. 10 to the minus 9 seconds or shorter. Does that make sense? So any good fluorophore has a very short fluorescence lifetime. Yeah. So that means that you can pour light onto this thing, and roughly every nanosecond, it's going to be shooting a fluorescent photon out in some random direction, right? Does that make sense? So as this is spinning around, way out in our microscope and through our filters and our big old huge apparatus, we have a shot at observing the rotational dynamics of this single molecule only because it has it's really bloody bright. You know, it's a very, very bright fluorophore. So you can stick it under the microscope. You know, you stick it onto this protein under the microscope and you get this going. And I guarantee you that this feat of getting this protein into the microscope with this fluorophore on it, with this laser shooting on it, and the microscope up there happened at approximately 2:35 a.m. Because any sooner, and there's no way they would have gotten all this stuff together to film this rotation before 2:35 a.m. No science happens before 2:35 a.m. ever. It all happens between 2:35 and 7:30 a.m. And then people start coming in and messing everything up. I guarantee it. I guarantee it. So each 10 millisecond frame here, we could be getting as many as 10 to the 7th photons. But that's only in theory if we could collect every single photon and it absorbed every single photon that's incident, But really, we're probably getting more like 10,000 photons in the 10 millisecond window, right? But still, that is enough. That is enough to see the damn thing rotating. Okay, I've sort of sermoned off here too much. But are we on the same page? Yeah? Okay, Kai is nodding. Carla's writing. Hikun has the same damn expression he always has. What does that mean, Hikun? Does it make sense or no?
I'm still thinking.
Okay, all right. Okay, Adam, making sense?
Yes. Richard
Good.
has a side question in the chat.
Oh, okay. We have to watch again later. Okay.
Right above that.
Okay, how do they properly orient the single molecule again? Excellent question, I love that. So how do you orient a molecule? Well, first of all, you take advantage of the fact that, and I'm guessing here, but I bet it's the right guess. I'm guessing this is a membrane-bound protein, right? So you can make phospholipid membranes on microscope slides or cover slips, right? So you can bulk orient all these lipids onto a surface, right? Then you've just got to get these molecules into the membrane, right? Now, you're never just dealing with one. You've got an impure fraction of protein that's modified with an impure dye that's mixed up, and it's a big old trash heap, right? But you spread it onto a microscope slide, and you do all this stuff to try to ensure that there's a possibility of a single one of these molecules in that membrane that's sticking up in the right orientation, that you can see this, right? Does that make sense so far? Now, then you're in this weird conundrum, right? Because you see this sort of blinking on and off. Mostly you see trash. You see fluorescence, you see aggregates, you see non-flashing lights, you see all kinds of weird filaments and hair and spit and all kinds of stuff in your microscope. But occasionally you see a point in point here that's sort of going bright, dark, bright, dark, bright, dark, bright, dark, bright, dark, right? You say, aha, this is my F1 ATPase, right? My Cy3 modified F1 ATPase, right? And it might be, or it could be the goddamn 60 hertz noise in the building messing with your camera. But if you can do this a couple, 3 nights in a row, or, a couple, 3 nights in a month, right? And you get approximately the same result, right? You get approximately the same frequency, etc. Then you can say, aha, there's something in here that is consistent with this cartoon, right? So you don't actually ever know that this is what's going on. All you do is you set up the conditions such that this is possible, and you look, and if you see something consistent, with one of these guys rotating around, then you declare victory. And then you get go to the protein database and you get this picture out, then you make a little purple one in ChemDraw and you make that and you paste it together. Then you go find a stupid ass clip art of a light bulb and magnetic field lines, which is not even true. And you put that on top. Then you use the Microsoft Art Draw tool thing and you make a circly arrowy thing like that and you stretch it on there to indicate that it's going around. And then you make a stupid shadow underneath, but there's no goddamn shadow because these are all transparent. But you do all this stuff so that you portray, so that you can deceive your viewer into thinking this is exactly what you have here, which it might be, but there's really no guarantee. Does that make sense? That is how science is done, guys. So now let's move on to the next foil here. Now this is a fluorescence resonance energy transfer. It's a FRET process. Okay. Now FRET is something you're not supposed to do. Did you get that one, Kai? Or no? Don't fret.
Fret?
Don't fret.
Oh, yeah.
Fret is English, right? Oops, hold on. Fret is.
Don't worry.
Yeah, fret means worry, right? Exactly. So don't fret. We're going to talk about fret. Okay. So in fret, let's say you have a couple of molecules, right? And in stilbene and stilbazolium, we talked about them. Because that's a good example where it's easy to draw the resonance form that has a transition dipole. So I'm going to draw that for you again. All right. There's a stilbene. This is the fluorescent dye. It's red. It's beautiful. Everything's good. They put all kinds of cabbage on this nitrogen and this one, but this is the base unit for the stilbene dye. Right? And when this is excited, the resonance structure changes to this. So the nitrogen normally has a lone pair, and this guy has two lone pairs, and it's a formal negative charge, right? So this is a case where this is called a Lewis structure, right? Which has two cool features. One, it tells you where the atoms are. And two, it tells you where the bonds are, right? Now, Lewis should be canonized because these things make sense, you know? Goddamn Lewis structure, it always makes sense, right? Can you look at this Lewis structure, Calvin, and sort of tell me, like there's this nitrogen that has 3 bonds, one lone pair, and this is neutral, right? And now there's two bonds and two lone pairs as a formal negative charge. And that makes sense, right? You know, basically the charge came down from the nitrogen and click, 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 and it ended up here on this nitrogen, right? You can push arrows. And the organic chemists would be completely at sea were it not for Lewis structures working really goddamn well. They're not perfect, but they work really well. They are one of the pleasantest fictions in chemistry. You know, I love them. Of course, they're sort of a lie, but I love them, absolutely. So this guy here has a huge dipole moment in this direction, right? Now, the thing about this is that if you have an excited state stilbizolium here next to a ground state one, this dipole moment can literally hop to the next molecule. And that's called resonance energy transfer. And there's different mechanisms. There's the Forster mechanism, there's the Dexter mechanism, and I don't really know that much about them. You know, there's different distance dependencies to them. But if you have an array of these guys, it's called an exciton. Right, a two-dimensional or three-dimensional crystal, right? And excitons are why dimolecules quench, right? Because you can excite them, and then the excited state energy hops around the crystal until it hits a defect and it goes away. It doesn't emit light, which is the whole point of the Smiles paper, that they sort of defeated the excitation quenching in dye solids. You know, the dye, it can make solid dyes that were still bright. But so an exciton, if it's in an array, it's a Forster or Dexter energy transfer. Oops. Energy transfer mechanism between any two dimolecules. Right. And so what is happening in these cases, right, is that you have, I'm going to copy this molecule down here in a schematic sense, right? We'll just do right. We'll give it a charge there, right? This is the excited state, right? And now this excited state with its neighbor molecule here it can simply transfer that energy over and this is a FRET phenomenon. And FRET stands for fluorescence resonance energy transfer.
I thought it was Forster resonance energy transfer.
I'm sorry. These questions must be settled in the cage.
Thunderdome.
In the Thunderdome, right. I don't know, to be honest. I've heard FRET as fluorescence, but
I think it's both, yeah.
I'm sure Forster works just as well, yeah.
Someone corrected me on that. That's why I was like,
Oh my God, really? Who corrected you?
I had a presentation on FRET, so I had to.
It was a biochemist who corrected you, right? Or biochemist or a physical chemist, right? You're not going to say?
I can't remember.
Okay. Because I like to diss on the biochemist, but I can't really diss on the chemist because they're always going to know some crap that I don't know. But the biochemists, you just get a little bit physical and you got them out of their depth and you can dunk on them, you know? But the chemists, you got to be really careful because they'll dunk right back on you and you're going to lose the game. So a FRET phenomenon, fluorescence or Forster, but I don't think it could be Dexter. It could be a different mechanism. But so let's just generalize.
There's like a lot of resonance, aren't there?
Yeah, there's the only two well documented mechanisms that I've heard of are Forster and Dexter. But there could be others. I'm sure there's others.
Yeah, I was reading about they're not official resonance transfers, but you can quench the energy with other like metal or MLCT or something like that, or the opposite, ligand to metal transfer. So it's just there's a bunch of different like named ones.
Well, so I don't want to mix too many metaphors here because MLC and LMCT, these are ways of a molecule that absorbs energy and transfers an electron from a metal to a ligand or a ligand to a metal, right? And then the relaxation of those states could be by a Forster or a Dexter mechanism or something like that. And it could be that in any particular case, oh, that's Forster, Therefore, in that case, FRET means Forster, but who cares? In this case, I'm just using FRET in a general sense. So this is what FRET is, right? Now, going back to the, let's see here. Going back to this guy here, this exemplifies it. So first of all, just to disabuse us all of any notions about the how brilliant and elegant and wonderful it is to do science. This fucking shit happened at 3:37. I guarantee it. And this the graduate student who got these data was strongly considering working at McDonald's for the rest of his life. Because he did not even have a fucking paper up to this point. And he was in his 4th year and he was shitting his pants. Right? He was distressed, And then he basically got all this shit together. And this one's a little bit easier, right? So this one can be done in a gel or a free solution, even possibly. Free solution's a little bit too mixy, maybe in a gel. But all you got to do is get these molecules together, right? And then you focus your laser onto them using a microscope objective, right? You scan that baby around, and then when you get a signal back, then you stop moving anything, right? And you watch that signal, right? And this is a 3-color experiment, right? They've got, for example, a blue laser Then they've got a green detector and a red detector. Right? So the blue laser can come in and it can excite, okay, it's not quite right. Okay, so the blue laser can come in and it can be absorbed, and then that blue radiation is first transferred to green and then to red in the downhill energy landscape of these two dyes, right? You know how when a molecule absorbs a photon, a fluorescent molecule absorbs a photon, the first thing it does is take a crap and give away 20% of the energy to the vibrational modes of the molecules around it. You guys remember that? So let me go through this real quickly. I've been trying to give you sort of a kinetic understanding of this, right? So hold on. Oops. Ah, here it is. Good. So so you've got this ground state, right? And then it absorbs a photon if there's a state up here, right? And then that state relaxes down there, right? That's generally the first thing that happens. Because there are these vibrational levels within that electronic manifold, the first thing it does is poop away that much energy, right? So if this is blue, then this would be green, right? And and then it also poops away some on this end too, right? Because it lands here and then it decays there. But so let's just say that this arrow here is green, right? Now, another thing can happen is that this state can dump its energy into the vibrational manifold of another dye here, right? And that'll relax down here. And this guy will drop down there and then poop out that energy. But this downward arrow here, this will be red. And so this is an or, right? It either drops down there or it transfers. This is a fret. And then that state emits. Make sense?
So every time we have that kind of emission, is it always going to be at a lower wavelength?
A longer wavelength, yes.
A longer wavelength, gotcha.
Yes, yes. Yep. That observation was made by Louis Stokes. I think it was Louis. Anyway, somebody Stokes. So it's called a Stokes shift. J.J. Stokes. I don't know, some Stokes guy. Who can tell me who Stokes was? Somebody who's surfing the internet right now, not paying attention. Type Stokes shift into Google and you'll get like somebody Stokes. And he did a bunch of work on fluorescence here, kind of trying to figure out what fluorescence was, And so now the thing about this experiment right now is that in order to do this fret thing here, the molecules have to be close together. Right, the two dimolecules, and this is called the donor, and this is called the acceptor. Right? The dimolecules just have those names, right? Because the photon, this is lambda EX, goes into this, and it just say, for example, it's blue, right? And then if this emits green, so you can say if EM is green, then the molecules are far apart. Oops. You know, on the molecular scale, maybe they're more than 2 nanometers or something. You know? But if the EM is equal to red, then the molecules are in close proximity.
Dr. Tara, I have a question.
Yes.
So this phenomenon would only happen, or you'd only see the red if the acceptor was a fluorophore, correct?
Right. Right.
So if it was not, you would just that's the quenching effect that you would.
Right. Right. Yeah. So quenching can happen by a gazillion mechanisms. You know,
Right.
can happen by a water molecule or whatever. It just kind of has to hit the donor in the right way, and it dumps out the energy somehow, right?
Okay, so this would be another form of a quenching if the acceptor,
The acceptor, that it quenches the donor.
Right.
Absolutely.
Okay.
Absolutely. But this is a sort of a special quencher, right? Because it quenches the donor and takes the energy,
right,
and then re-emits the energy at a new wavelength. So another thing that these are called, they're called molecular rulers, you know? Because they rule the molecular domain. Because they're like rulers, because they have like, a distance associated with them. That kind of ruler, not Benito Mussolini ruler. So that's another. Sometimes you see that coming up, like anybody who measures a distance using chemistry or physics says they've designed a molecular ruler. And it's like, oh God, give me a break. You didn't fucking design anything. You got lucky. You threw spaghetti at the wall so long that this one's stuck, and then you drew a target around it, and then you claim to have built something when you have no idea what you were doing after that. Okay, I'm exaggerating. Okay, so in this molecular ruler, right, what we see is that there's this red channel and this green channel. I think these are probably so the red channel is for this dye, the light coming through and fretting, right? So this is the docked and the undocked folding state of this ribozyme. Tetrahymena ribozyme, whatever the hell that is, right? Right? And if it's docked with whatever thing is causing it to dock, the substrate S, right? Then, in that case, the light that's absorbed by the laser transfers, and it's emitted on this red channel, right? So the red is high, and the green is low, because this blue one actually emits in the green, right? And the green one emits in the red, or something. No, I don't know. Anyway, I think the green one. So here's the psi 3 and the psi 5, right? So the psi 3, it's up here, it's outside of fret distance, and there it's inside of fret distance. There's also orientation to take into account there, right? The transition dipoles have to be aligned, because like when one dipole, it can do work on another, but not if they're oriented at right angles. You know, they can't really work on each other except by a magnetic mechanism, which is super, super weak, right? But if they're lined up in some way, then one can work on the other. So there's orientation and proximity effects, right? Now here's docked, undocked, docked, undocked, docked, undocked, docked, undocked, docked, right? This is over 30 seconds, right? This is one of the nice things about a lot of these biochemical dynamics, is that they're slow, right? So now, could you, using this information, calculate capital K dock, little k dock, and little k undock? Could you do that using this information? And how would that differ from the approach you would take to doing that using an ensemble average? Not a single molecule spectrum, but an ensemble average. That is our food for thought for the day here. So let us, I posted yesterday's notes on the on Canvas, and I'll post tonight's too. But I would like actually to talk a little bit about calculating dynamics using single molecules and calculating them using ensembles. Because 99.99% of what we are trained as chemists to do is on ensembles, right? So, oh wow. Oh, that's weird. I get it. Okay. So, capital K EQ for any reaction is actually always equal to little k forward over little k reverse, right? For A goes reversibly to B, right? And a k forward, a k reverse, right? And just thermodynamically, these are the relationships, right? So now, capital K EQ is equal to, on average, the concentration of B over the concentration of A, right? But in the fret case, what we're getting is, let's say this is docked. And B right? And so basically what we have here, we have to say, well, KEQ will equal the time spent in the dock state divided by the time spent in the undocked state, right? And if you have B and A, those concentrations, you can calculate that, right? But what about little kf, little kr? Okay. So I guess I'm asking a couple of things here. One is I'll offer that you can calculate capital K using these two times, right? Or by using these two concentrations, right? So for example, if you had, there's a bunch of different ways you can imagine getting the concentrations of these two species. It might not even be spectrophotometrically. It could be through an enzymatic turnover or I don't know. There are different ways to do it, right? So if you know the concentration, this might be 2.7 times 10 to the minus 6 molar, and 1.4 times 10 to the minus 8 molar, And so this, these two concentrations here will give you KEQ, which is, going to be approximately 2 times 10 to the 2, about 200, right? Maybe 190, right? But there's a decent estimate, 200, right? So, but what if you have single molecule data on which to calculate this, right? Then you can look at each individual state, the fluctuation between these two states, right? And you actually see it very directly. So you can ask how frequently in inverse seconds does A turn into B, and how frequently in reciprocal seconds does B turn into A. That's another way of asking those same questions, And you simply have to look at the data and measure, okay, so the A state lasted 2 seconds, and then it changed, and then it lasted 3 seconds, and it changed. Then it was 1.5, and then it was 3, and then it was 2, and then you'll get a bunch of average lifetimes, right? And then you can say, well, the B state, it averaged only 0.3 seconds, 0.3 plus or minus 0.1, right? So you can look in the lifetimes that these states last. Does that make sense? That's sort of a transition from the, it's sort of like a transition from thermodynamics to statistical mechanics, right? Thermodynamics to statistical thermodynamics, right? So one deals with the average properties of a solution, the concentrations of something. The other deals with the properties of the constituents, right? How long does a particular constituent last? You know? So let's finish today off with a question about big K. And let's say that you know that KEQ is equal to the negative exponential of the free energy, right? Right? This is a thermodynamic truism, right? So this tells you the overall free energy change of a reaction. But nothing about the rates. So I can think of a very common chemical reaction for which we know the thermodynamics. We know the equilibrium constant, and we know that this is an exoergic, it's a negative free energy reaction in the atmosphere, right? And this reaction is the reaction of oxygen with nitrogen, right? O2 plus N2 makes, or N2 plus a half O2 makes N2O. Or 2N2 plus 1O2 makes N2O, for example, makes nitrous oxide. Or N2 plus O2 makes 2NO, 2 nitric oxides. Or there's N2O4. There's a lot of different nitrogen oxides that you can make with the atmosphere, right? And I think it's a fair question to say, well, how the hell do we have breathable air then? If the atmosphere is going to friggin' break down into nitrogen oxides, got 80% nitrogen, 19% oxygen, the air is toast, according to any classical thermodynamics, right? But the rate constants are, the forward and reverse rate constants are effectively zero, right? So you can have, as an example, you can have O2 plus N2 makes 2NO, right? 2 nitric oxides. It's a radical species, but it's very common, very well known molecule, right? And then there's N2O and NO2 and the list goes on, you know? There's a lot of different nitric oxides. We could take any one of these reactions, call this K1, right? Capital K1, you know, could be on the order of, let's say that it's, you know, 10 to the minus 6. You know? Let's say that it's actually significantly endothermic, you know? So that means that, you know, delta G naught is equal to minus RT log of K. I'm sorry, log of capital K, right? Right. And so that will be, you know, this will be, you know, probably, I'm not exactly sure, maybe, you know, minus 50 kcals or something like that per mole. I'm sorry, plus 50 kcals per mole, right? So, but this means that about 1 in a million molecules in the atmosphere should be NO, right? Nitric oxide. But that's not observed. Because capital K1 is equal to K1F over K1R is equal to a super G D small value over an even super G D small value. And thank G for small values. And short lectures, which this was not. You want me to put these notes up there? Cool. I'll put them up there. Also, I want you to know that this is what I had ready for you. Oops, here, I'll put it down here. Pop quiz. But I didn't give it to you because I saw 4, 5, 10, 11. I saw at least 11 faces, not including Lily, Leslie, and Pauline, who better start showing up here eventually.
I'm here.
I know. It's okay. I'm just joking. You never have to show
I'm
up.
sorry.
It's okay. I miss you. It's okay.
Miss you too.
Oh. See, Pauline, some people are super polite.
Unlike you, right, Dr. T?
Oh, sorry, you reminded me of something. I'm not polite either. Okay.
I was writing in the chat. I have really bad Wi-Fi.
Oh, you did. I'm sorry. Now I'm a bastard, right? I'm trying to be funny by picking
Of course
on you.
not. Of course
Now
not,
I'm a
Dr. T.
bastard.
Of course not.
I'm a bastard. Let's face it.
Of course not.
Okay. I love you guys. I'll see you guys on Thursday. And we'll
Love
have a
you too,
quiz or
Dr. T.
something. Okay, bye-bye.
Thank you.
Bye.
Bye.